Hello everyone, and welcome to this week's edition of the HoloTube. We are very happy to have Dominic Else from the Perimeter Institute, and Dominic is going to tell us about holographic effective field theory for a metal with a Fermi surface, as you can read from the slide. So Dominic, we're happy to have you. The screen is yours.
Thank you. It's my great pleasure to have the opportunity to tell you about this work I did recently. So by the way, you feel free to ask questions during the talk. You don't have to wait till the end. So I don't really think for this audience I need to explain what holography is, but obviously, so quantum field theory in d space dimensions can be dual to a quantum gravity theory in one higher dimension. In this talk, I just want to consider the limit whether quantum gravity theory is weakly coupled, so you just solve the classical equations of motion, which presumably is going to be dual to some kind of strongly coupled quantum field theory, maybe in some kind of large n limit or something like that. And specifically in this talk, I want to consider the problem of understanding strongly coupled metals from this point of view, also known as non-Fermi liquids. Okay, just to say that there is strong practical reasons why we should try to understand non-Fermi liquid metals. There are many materials in which we do see this non-Fermi liquid behavior. A famous example is the high TC cuprates, such as YBCO, which originally became famous because they host high temperature superconductivity, but there's a lot of other interesting stuff going on in the phase diagram. So this is a vastly oversimplified phase diagram. But specifically what it shows is that above this superconducting dome in temperature, you have this regime that people have called the strange metal. And so there's various diagnostics that you can look at, and it's very clear that whatever is going on in this strange metal is not weakly coupled or Fermi liquid physics. It's going to be some kind of strongly coupled physics that we need to try to understand. And despite the fact that these materials have been studied now for decades, and people have been thinking very hard about how to understand this strange metal theoretically, I would not say that there is any satisfactory theory at the moment, even still now. It's one of the big open problems of our field. And part of the problem, of course, is that it's understanding strongly coupled systems in general is not so easy. So that's where you might think that holography could play a role. And then it's not just these materials. There are a lot of other materials where people see non-Fermi behavior. There's like heavy fermion materials. Twisted bilayer graphene is a very hot topic nowadays, and it's also seen in that kind of material. Okay, so we need a theory to understand these non-Fermi liquids. And at the moment, we don't have enough theory yet. So this is the only experimental slide I have, but just to show that there are reasons why we should be studying this problem theoretically. So in the rest of the talk, I want to follow this outline. So I will start by reviewing, what are the most fundamental properties of metals that we want to be able to capture through any model of a metal, whether it be holographic or any other kind of model. And then I will review the previous discussions people have made in the literature about holographic models of metals and discuss some potential drawbacks of those models. And then I want to present a new way to construct a holographic model of a metal, which is quite different in perspective from the previous literature. And the key idea is that we just think of it as constructing an effective field theory. I'll explain what that means. And then I will present the result that we obtain from solving this model. So what are the fundamental properties of metals? So to answer that, I maybe first need to explain, what is the definition of a metal? So in this talk, I will take the following definition. So in the UV, I assume that we have some quantum field theory with a global U1 symmetry and continuous translation symmetry. And then I'm going to say that I'm switch on a non-zero charge density with respect to that the charge of that global U1 symmetry. So there's many different possibilities you could think about. For example, you could just consider non-relativistic electrons where you switch on the chemical potential. You can also consider some relativistic system if you prefer. Now, of course, in condensed matter physics, normally the UV would not be a quantum field theory, it would be just some kind of lattice model. And in particular, it would have only discrete translation symmetry, lattice translation symmetry, rather than continuous translation symmetry. But that distinction turns out not to be very important for the specific things I want to discuss today. So I figured to keep things simple, I will just assume that we have this system that has a continuous translation symmetry. So that's the UV, but so when I switch on the nonzero charge density, we'll presumably do some kind of RG flow. So it'll flow to some IR fixed point, which we call the effective field theory that controls the low energy or IR physics. And basically any IR theory that's compatible with this UV requirements, these UV properties, I'm going to call it a metal. That's a very, very general definition of metal, which can apply to many different kinds of systems, and they could be strongly coupled. And one slightly awkward thing about these definitions, I kind of have to exclude superfluids by hand, because otherwise they would also satisfy this definition. But if you do that, everything else I'm going to call it a metal. And so what is the nature of a metal? Well, we could start with the simplest case, where you just have non-interacting electrons. So free fermions, if you like. And then the Hamiltonian, you can just diagonalize the Hamiltonian, you just write it in terms of the single particle occupation numbers. So these NK are the single particle occupation numbers, which since you have translational symmetry, they're labeled by the momentum. And then you have some amount of charge that you want to accommodate. So you'll fill up the lowest energy single particle states. And the boundary between the occupied states and unoccupied states is the Fermi surface. So Fermi surface is where all the low energy excitations live. So if you add an electron near the Fermi surface or a hole near the Fermi surface, those are the low energy excitations. So you already see that this is a different kind of system from the kind of quantum field theories that people generally discuss in particle physics, because there's a whole surface of gapless states. In a relativistic system, normally the gapless states would exist only at k equals 0. But here they exist on this codimension 1 surface in momentum space. So it's in some sense they're much more gapless. And then there's this relationship between the charge density that you imposed and the volume enclosed by the Fermi surface. In these non-interaction systems, that's kind of just a trivial statement, but as we'll see, it becomes more non-trivial when you start talking about interaction systems. So the simplest way to switch on interactions is this so-called Fermi liquid theory. And so in Fermi liquid theory, you only write down a very special kind of interaction, which looks like this. So basically, it's still diagonal in the occupation numbers of the single particle states. And so what that implies is that this story that I showed you before pretty much carries over. You still have, in the ground state, you still have some set of single particle states that are occupied, and the other ones are unoccupied. The Fermi surface is the boundary between them. And again, the low energy excitations are particles and holes near the Fermi surface, which we generally call quasi-particles in Fermi liquid theory. So then you might say, well, why do we switch on this very special kind of interaction? A general interaction term you can write down is going to scatter from one momentum to a different momentum. So it won't preserve these single particle occupation numbers. And so that's true in the UV. But what you can imagine is that maybe the other interactions that you could write down are irrelevant in the renormalization group sense. So as you flow from the UV to the IR, it could be that all the other interactions just disappear. And this Fermi liquid theory would be like a fixed point under the RG flow. And indeed, if you set up the RG, you can argue that it is a fixed point. The question is, does the system flow to that fixed point, or does it flow to some other fixed point? But one thing I can say is if you do flow to Fermi liquid fixed point, you still have this relationship between the UV charge density and the volume enclosed by the Fermi surface. Now it's called Luttinger's theorem. So here's a much more non-trivial statement. It's some statement about some quantity that's that the RG flow remembers. So you have some UV property, which is the charge density, and it's related to an IR property, which is a volume enclosed by the Fermi surface. So as I said, the question is, if we start with a UV system that has these properties, which is how I defined a metal, does it flow to Fermi liquid fixed point, or does it flow to some other strongly coupled fixed point? And so certainly we see experimentally that there are many materials where it does seem to flow to Fermi liquid theory, and Fermi liquid theory is the correct description of the IR dynamics of the system. But as I already mentioned, there are other systems, other materials where that's not the case. So presumably you flow to some strongly coupled fixed point, and that's what we would like to understand, the nature of that strongly coupled fixed point. So now you can ask, what are general properties that this non-Fermi liquid metals have to have? Now that we're going beyond Fermi liquid theory, if they're going to be describing a metal. And so here I'll just make some assertions. I mean, there's a whole set of arguments I can discuss for why we believe these things to be true. But basically, they should still have a Fermi surface in momentum space. So I'm being a bit vague about what the Fermi surface is here. In the case of Fermi liquid theory, it's the surface in momentum space where the quasi-particles live. But in a beyond Fermi liquid, you won't have quasi-particles. So it's maybe a little bit more unclear what exactly we mean by Fermi surface, but there is always a Fermi surface where something happens in momentum space. And the other statement is that the Fermi surface still obeys the Luttinger theorem. So it will still be true that there's a relationship between the UV charge density and the volume enclosed by the Fermi surface. In some sense, the fact that you have a Fermi surface reflects the fact that you're at non-zero charge density via this relationship. So now I will review a bit about the previous holographic models of metals that people have discussed. So my reference for this was always this really nice book, which has a very comprehensive reference list. And so generally what people do is that, so you start with this continuum theory with non-zero charge density. For holography, it's probably easiest to say that it's a CFT, because that's what we know is dual to some ADS geometry. And we perturb it by chemical potential, which will put it at non-zero charge density. And then that's going to induce an RG flow to some IR effective field theory, which should be a theory of metal given your starting point. And so more precisely in holography, so in this talk, I'll always just assume that the metal that we start trying to describe is in 2 space dimensions or 3 space-time dimensions. So then the dual geometry will be in 3+1 space-time dimensions. So if we start with a 3D CFT, we know that it's dual to some ADS4 geometry. But if we switch on non-zero charge density, that's like switching on an electric field in the UV region of a space-time. And so now the ADS geometry is not going to be the solution away from this asymptotic region, because the metric backreact, the electric field backreacts on the metric. You have to solve the Einstein equations coupled to the electromagnetic field. And so in the simplest case, you get this ADS-Reissner-Nordstrom metric, where the bulk spacetime terminates in a charged black hole. Okay, although this is the simplest kind of model, there are issues that you can worry about. One thing that's been a lot discussed is that because the black hole has an entropy density, you have to interpret that as the entropy of the dual quantum field theory. So there's in the simplest version of this model, you find it there's a non-zero entropy density, even in the limit of 0 temperature, which is pretty weird. RUB would contradict the third law of thermodynamics. There are more complicated versions of this model where you can eliminate this entropy density, although sometimes that introduces other problems. But anyway, for the purpose of this talk, I'm not so worried about that. But what I am worried about is the Fermi surface. So there is not much trace of a Fermi surface that satisfies Luttinger's theorem in these systems. So that kind of contradicts the general claim that I made, that you still always should have a Fermi surface obeying Luttinger's theorem. I guess there are some arguments you can make about there's a small Fermi surface, much smaller than it should be, according to Luttinger's theorem. But the bulk of a charge, which is majority of a charge, which is kind of hidden behind the black hole event horizon, doesn't seem to be reflected in the Fermi surface, at least at the level of doing classical calculations in the bulk space-time. It's probably true that if you actually take into account quantum effects in the gravitational theory, that the Fermi surface will come back. I mean, it's hard to see how anything else could happen because we do have these general requirements. But that is concerning from the point of view of, the point of holographic description of quantum matter was kind of supposed to be that you only have to do classical calculations in the bulk to describe a strongly coupled quantum field theory. And the Fermi surface is so essential to physics. I find it rather worrying that you cannot describe it from a classical computation in the bulk. It makes me think that probably the key physics of the metal is not being captured by at least by the classical limit of the bulk. And so people study these models a lot from the point of view of like they compute transport and things like that from classical calculations in the bulk. But I'm concerned whether this is really capturing the right physics at all, because the actual real transport properties should be dominated by the Fermi surface. So I'm not sure that these calculations are actually capturing that at all. Maybe it is in some secret way, but I don't know the answer to that. And I should mention there are these other kinds of holographic models people have discussed whether charge matter is not inside a black hole, it's just kind of sitting around in the bulk geometry. As people call these electron star models. So in these systems, you do have some kind of Fermi surface at a base Luttinger's theorem. There are some other challenges, I think, with extracting useful physics out of these models, but I don't know too much about that, so I won't go into that.
Dominic, there's a question in the chat.
Yeah.
What would be the effective speed of light in the bulk gravity other than the Fermi velocity? And does this setup allow for any faster than speed of light propagation? Was the question from Petro.
Well, there's certainly no faster than speed of light propagation on the bulk theory, so I don't think they can be on the boundary theory. As for the question of what the Fermi velocity is, well, because there's no Fermi surface, I'm not sure to what extent you can answer that, but if there is a Fermi velocity, I assume that it's the speed of light, because it's...
Yeah, the question is what in the field, I guess...
Matthias, can you pose the question? Because was it a question only to you? Or?
I think it went only to me as the host. So Petro, feel free to jump in and clarify if you can.
Or post it for everyone. There is
I'll copy, paste, assuming that's okay with Petro.
Yeah, okay, maybe.
So here's the question.
Yeah, I mean, I definitely don't think there can be any faster than speed of light propagation, because I mean, ultimately you're describing some CFT that's perturbed by charge density, and clearly such a system, some relativistic CFT. So clearly such a system cannot have faster than speed of light propagation.
Mm-hmm.
I think if there is a Fermi velocity, it will just be set by the speed of light in the bulk theory. That's definitely what happens in the, as you'll see later, like it's what happens in my new model, which I will discuss. So.
Mm-hmm. And while we're talking, can I ask you, there was the idea of hidden Fermi surfaces in these models, right? So that was investigated by Hartnell and friends and Lisa Huys at the time. So this I thought that was one way to explain that there were Fermi surfaces, but they were not accessible. Are you don't seem like you wanted to talk about that.
Well, I mean, yeah, I mean, there may be something like that. I have a little bit of trouble with those proposals in the sense that I know from general arguments that there are only very specific ways that a Fermi surface can be hidden. Like, for example, when it's charged under some gauge field, and I don't know how to fit these models into that story.
Okay, thanks.
I mean, what may be true is that a Fermi surface is hidden only in the large N limit and then becomes unhidden, which is again because the large N limit corresponds to the classical limit of the gravitational theory. So it comes back to this idea of the Fermi surface is not accessible in the classical limit.
Yeah, thank you.
Yeah, no problem. So, sorry, I'm having some, yeah. Yeah, so, okay, that's all I wanted to say about the old models. Certainly I haven't probably done justice to them. But anyway, the point is that there are some issues of these models, and I want to present a new approach which may have some advantages. So to motivate this new approach, I want to take a step back and ask, what are we really trying to do here? So as I mentioned, the idea is that you should start with some continuum theory that has these properties, and it will flow to some IR theory, which would be a theory of the metal. In these previous holographic models, if you look at what they're really trying to do, they're trying to find an exact holographic description of this whole RG flow. Because we know that in holography, like the extra spatial dimension you introduce is interpreted with respect to the dual quantum field theory as an RG scale. So the fact that you're trying to describe the entire geometry, starting with this like asymptotic ADS region with the electric field, tells you that you're trying to describe this whole RG flow. Now, this is very different from what we normally try to do in condensed matter physics. So in condensed matter physics, what happens? At the UV scale, you have effectively some material like YBCO or whatever it is, and maybe you have some idea of what the Hamiltonian of that material is. For example, in YBCO, people often talk about the Hubbard model should be the lattice Hamiltonian that captures the physics. The problem is, even if you have a Hamiltonian, you have no idea how to solve that Hamiltonian. So it doesn't help you that much. But instead, what you can do is you can just say, well, whatever the Hamiltonian is, it's going to flow to some effective IR theory, which governs the low energy dynamics, and then you just try to work out what the nature of that IR theory could be, which ultimately, of course, you have to compare with experiment to see whether it's right or not. So the proposal is that rather than trying to find a holographic description of the whole RG flow, we'll just try to come up with a model of the IR theory from holography and not worry about describing the flow from the UV. Okay, but it does raise the question of how do you know if you have a good candidate effective field theory for a metal? Well, as I said, ultimately you want to compare with experiment, but in the meantime, you need to have some criteria that you can use. And so the idea is that we want the IR effective field theory to be compatible with these UV requirements that you have continuous translation symmetry, non-zero charge density, etc. But we want to be able to do that without actually solving this whole RG flow. So we need what is often referred to these days as an emergeability condition. You need some condition on the IR effective field theory that allows it to be compatible with these UV requirements. So understanding these emergeability conditions, I think, is a pretty general question of great interest. in the specific case of this particular characterization of a UV, we tried to give the answer in this paper that we wrote. And so I will take a bit of a detour now to summarize the answers that we gave. So when we split up this UV requirement into two halves, so we have firstly the statement that you have this global U1 symmetry and continuous translation symmetry, and then the other statement is you have non-zero charge density. So the statement about symmetries, it's kind of obvious how that has to correspond to the IR. The UV symmetries have to act in some way on the IR theory. I mean, technically, I guess it could be a trivial action, but at least you need to have some homomorphism from the UV symmetries into the IR symmetry group. Now, the non-zero charge density, that's a trickier thing. So if you were very naive, you would say, well, if a UV is at non-zero charge density, then the IR should be at that non-zero charge density as well. But that doesn't make sense because the charge density is not an invariant under an RG flow. Because, in RG flow, you rescale space. Clearly, the charge density is not going to be invariant under that. So, okay, this is not the right condition. So let me try to tell you what is the right condition. And so I'll illustrate this in this simple example of an electron gas in one spatial dimension. And so, for example, you could just start with the Hamiltonian of non-interacting electrons in one spatial dimension. And so if it's non-interacting, we can solve it exactly. So we can, even in the UV, we can solve it. And so we know that you have this dispersion relation for the single particle states. And then since you have some non-zero charge density, you have to fill up some single particle states. The Fermi surface in a 1D system is just 2 points, KL and NKR. Okay, but how about the IR theory? So the low energy excitations, they all live near this left Fermi point or the right Fermi point. So to describe the IR, we can just linearize the dispersion relation about those points. And then if you do that, you'll see that this spheric system is actually just equivalent to a 1 plus 1D Dirac fermion at 0 charge density. So the IR theory of this electron gas is just a Dirac fermion at 0 charge density. And again, the charge density is not an RG invariant, so that's why it's okay for the UV and IR densities to be different. Then the question is, how does this IR theory reflect the fact that the UV theory was originally at non-zero charge density? And so it ends up being related to this fact, which is well known, that in the Dirac fermion, you have this more symmetry in the gapless case. You can say you have the original U1, and then you also have the axial U1. Or equivalently, you can say that you have the left-moving U1 and the right-moving U1. In any case, the point is that there's more symmetry here than there was in the UV. You have two U1s. So that's because it's symmetry of the IR theory, but it's not a symmetry of the UV. That's what we would call an emergent symmetry. And this emergent symmetry also has this interesting property, which has various names, or sometimes called the chiral anomaly. Basically, if you apply a background electric field, then the left and right moving charges are no longer conserved. The total charge is still conserved, of course. So this is an example of a more general thing that people call 't Hooft anomaly, which is where the charges become non-conserved in the presence of a background gauge field. So it turns out that this two properties. In fact, you have this emergent symmetry, and in fact, you have this anomaly of the emergent symmetry. It's what allows this 1 plus 1D Dirac fermion to be consistent with the UV theory at non-zero charge density. And so it's a similar story in higher dimensions. So let's consider a Fermi liquid in 2 spatial dimensions. So this is the Hamiltonian I wrote down for the fixed point, RG fixed point. And this fixed point Hamiltonian has a property that the charge at each point on the Fermi surface is individually conserved. So this is very many conserved quantities, actually. It's infinitely many conserved quantities. The emergent symmetry group that corresponds to that is also infinite dimensional. Technically, if you want to be very precise, it's this thing which you call a loop group, which is the group of smooth functions from the circle into U1, or also known as LU1. So again, this is an emergent symmetry because there are irrelevant operators you could add to the Hamiltonian, which would break the symmetry, but they flow to zero under the RG flow. And then this loop group also has an anomaly. I won't get into exactly how we define that. And it turns out that the fact that you have this emergent LU1 symmetry and anomaly is precisely what allows it to derive Luttinger's theorem. That's what we showed in this paper. So any system, even if it's strongly coupled beyond Fermi liquid theory, as long as it has this emergent symmetry and anomaly, you can derive Luttinger's theorem from that. So Luttinger's theorem, remember, is this relationship between the UV charge density and the volume enclosed by the Fermi surface. And the fact that you have a Fermi surface is kind of encoded in the fact that you have this emergent LU1 symmetry. And so again, this is what allows the system to be compatible with non-zero charge density, because generally the Fermi surface volume will be non-zero. So therefore, the UV charge density will be non-zero. So this kind of answers this question which I posed of what is the emergeability condition that we want to impose. What we want to impose is this IR effective field theory should have a global LU1 symmetry with 't Hooft anomaly. So then all we need to do is we need to impose that on our holographic model. And fortunately, that's easy to do via the standard holographic dictionaries. And we know from that dictionary that if you want your quantum field theory to have a global symmetry, that should correspond to putting a dynamical gauge field in the gravitational theory, which couples to the metric. And then I also said that we want this LU1 symmetry to have a 't Hooft anomaly. So that under the dictionary maps to a statement that we have in the action for the bulk gravitational theory, we have to write a Chern-Simons term. And you'll see the form of the Chern-Simons term precisely later. So let me just be more precise about what all these things mean. So I said that we want a gauge field for the LU1 symmetry. So what is such a gauge field? So this is the definition of LU1. So we introduce this coordinate theta that physically parameterizes where you are on the Fermi surface, or mathematically just parameterizes this S1 that's in the definition of the loop group. And then the generators of the loop group are parameterized by this coordinate theta. So there's infinitely many generators because theta is a continuous coordinate, which corresponds to the fact that this group is infinite dimensional. The total charge of the U1 subgroup, which would correspond to the microscopic U1 symmetry, is the integral of the theta of these generators. So what is an LU1 gauge field? So let's say you have some space-time M and you want to define the LU1 gauge field on that space-time. Basically, you want to write down a vector field on that space-time, but the vector field is also continuously parameterized by this coordinate theta. And then the gauge transformation is the usual gauge transformation for gauge fields, but we allow the gauge transformation to also depend on theta. So if you look at this definition, you'll see that it's more or less the same as saying that you have a U1 gauge field on M times the circle. So we will kind of use that analogy, but you shouldn't take it too seriously from a physical point of view. It is important that you remember there's really a gauge field for an LU1 symmetry at the end of the day. And so, okay, I mentioned that we want to write down a Chern-Simons term for that gauge field. So Chern-Simons term looks like this. So because I wanted to originally describe a 2+1D metal, it means the bulk spacetime will be 4-dimensional, 3+1. And then this theta coordinate, which I introduced, also introduces this additional circle. So that gives us a 5-dimensional manifold. So on the 5-dimensional manifold, we can write the 5D Chern-Simons term. So because A is a 1 form, if you construct this product, it gives you a 5 form, which you can integrate over this 5-dimensional space. And then for various reasons, the level is quantized to be an integer. So that's for Chern-Simons term. And but let me emphasize that although it kind of looks like when in finding this action, we're treating spacetime as 5-dimensional, that's just a formal device. In particular, you should not say that there's a metric on this 5-dimensional space. The actual dimension of spacetime is 4-dimensional, and that's where the metric lives. This additional coordinate that we introduced is S1. It's not a spacetime coordinate, it's an internal label for the symmetry group. That's something that I think people often get confused about. Just to illustrate this, if say the symmetry group was not LU1, but it was just U1 times U1, you wouldn't say that because we have a U1 times U1 symmetry, we should define the metric on a spacetime that has 2 disconnected components. I mean, that wouldn't make any sense. But saying that the LU1 symmetry gives you an extra spacetime dimension would be exactly like that. So that's just not what we want to do. The S1 is a internal index label, not a spacetime dimension. And then another important point is that although we had this formal equivalence between the gauge fields, it's not true that having, and so here I'm really making statements about the dual quantum field theory. If you said that the dual quantum field theory had a global LU1 symmetry, which is to say there's a conservation law on some 3-dimensional spacetime, that's not the same as saying that the system lives on a 3-dimensional spacetime times the circle, and that you have a U1 conservation law on that higher dimensional space. So the difference is that if you have a U1 conservation law on this higher dimensional space, then if you write the continuity equation, it would contain this term like d theta j theta, where theta is the coordinate corresponding to this extra dimension. And j theta could be non-zero, so there would be some contribution to the conservation law from that term. But for an LU1 conservation law, there is no such term. So another way to say it is that the LU1 conservation law enforces that this current in the theta direction is identically 0. So that's a difference that we need to keep in mind. And the reason I emphasize that is that it's important for when we write the Maxwell term. So for the gauge field and the bulk, you want to write some kind of Maxwell term for it in addition to the Chern-Simons term. But you don't want to just write the Maxwell term as a 5D gauge theory. And the Maxwell term is going to be a Maxwell term for a 4D gauge theory, even though you integrate over the theta, but that's just an internal coordinate. So the metric that appears in the determinant is a 4D spacetime, and also when we contract these indices, we only contract over this 4 spacetime coordinates. So you don't contract over the Fermi surface coordinate. And that's necessary. It's necessary for a Maxwell term to be like this and not like the Maxwell term of the 5D theory, because if you did write the Maxwell term for a 5D theory, that would be due to having a structure like this, which is not what we want. So basically, I've pretty much defined what the model is. The bulk action is the usual gravitational action for the metric, plus the Maxwell term that I defined, plus the Chern-Simons term. And I don't claim that I can derive that action from some string theory or anything. I'm just going to postulate that that's the effective action for the bulk theory, and then say, what does that imply about the dual quantum field theory?
May I ask a question? How does the Chern-Simons term look? Because you just told me that the theta component of A does not exist.
Right. So this is what I hear. So I mean, the theta coordinate does exist, but it's not a space-time. But you can still integrate over it to define the action if you want. So that's what
you can integrate over it. But there's the A in this Chern-Simons term is has 5 components. But you just told me that in the Maxwell action, I should only have 4 components. So where does the 5th component of A come from? The A sub theta, the index theta of A.
Right. So that's a subtle thing. I mean, for most purposes, you can just say that I set that component to 0. And then, I mean, I can still write this action. I just consider the subset of vector fields where that component is 0. But I think there is some physical significance to that, a theta component. It corresponds to the at least in Fermi liquid theory, it would correspond to like the quasi-particle Berry's phase. As you move a quasi-particle around the Fermi surface, you can acquire a Berry's phase. This A theta precisely encodes that. But I don't think you can treat it as a dynamical field in the bulk theory. At most, it would be some kind of background field. Does that answer the question?
Partly, thank you.
Maybe just as a thought, when working with anomalies, then sometimes we promote internal directions like a U1 direction in terms of a coordinate that is promoted then to a real space coordinate. So maybe that is the spirit in which this is written down.
Yeah, I'm not sure if I am familiar with what you're referring to. I mean,
I can mention it later in the discussion. Thanks.
Okay.
It was just meant as a comment in case this made sense. I can explain more later.
Okay, great, thanks. Right, so yeah, so this is the action that we have. Yeah, just a few more bookkeeping things before I can present the solutions. So you also obviously have to specify the boundary conditions in the UV region of the spacetime. So I'm going to take the asymptotic metric to still be ADS. And then if you solve the asymptotic solutions to the equation of motion for the OU1 gauge field in this asymptotic metric, it looks like this, which is the same thing you would get for a theory without a Chern-Simons term. It turns out that the Chern-Simons term does not affect the asymptotic solutions for the gauge field, although it obviously affects it once you go away from the asymptotic region. So then you can just apply the usual holographic dictionary, the constant piece of the yeah, sorry, yes, this should be dr squared, not dz squared. R is like the radial coordinate that you introduce in the holographic spacetime. So the constant part of that asymptotic solution gives you the background value of the gauge field in the dual quantum field theory, and then the sublinear part gives you the value of the current in the dual quantum field theory. So that's the usual kind of holographic dictionary that we're familiar with. And then there are some specific things that we want to oppose on the dual quantum field theory, which will correspond to conditions on the gravitational theory. So you want to say that the charge density of the LU1 symmetry is 0. Although we want to describe a system that has non-zero charge density in the UV, but we're not trying to talk about the UV, we're trying to construct an IR effective field theory. So in the IR effective field theory, you want the charge density to be 0. And then there's also this subtlety, the Fermi surface has to enter somehow. And the way you say what the Fermi surface is, that is you apply this phase space magnetic field. So the LU1 gauge field, you can define this particular element of the curvature, which exists in the theta direction and the spatial direction. And we set that to be determined by the Fermi wave vector. So the Fermi surface traces out some function in momentum space as a function of theta that determines this curvature that we impose on the dual quantum field theory as a background. In some sense, you could say that this is encoding the fact that position and momentum are non-commuting operators. So because if a theta coordinate corresponds to moving in momentum space, there has to be some kind of non-commutation between the theta direction and the spatial direction, which is encoded in this quote-unquote magnetic field in phase space. So that basically defines the model. Now I'll just present what we obtained from solving that model. It fortunately ends up being quite easy to solve analytically. So specifically, one of the main things that we can compute is the Green's function of the LU1 charge density. So this is some linear response function that we compute as a function of frequency and wave vector, so omega and q. So the LU1 charge density is like corresponds to the generators of this loop group. So they're indexed by a coordinate theta. So that's why we have theta and theta prime here. In this particular model, it turns out that the result you get is just local in theta space. So you have this delta function here. And then, so there's this interesting structure you get here. So you can look at the fact that you have a pole at omega equals q perp. So here I've decomposed the wave vector into components parallel to the Fermi surface and perpendicular to the Fermi surface. You have this pole at omega equals q perp. So usually poles in Green's functions tell you they have some, propagating mode. And it moves at group velocity VF. Actually, the magnitude of VF here is just equal to 1, which is, I guess, the speed of light in the bulk theory in the units that I'm using. But the mode only moves in the direction perpendicular to the Fermi surface. It is not, it's chiral and directional in that sense. So this is also what you would get in a Fermi liquid, actually. But you shouldn't view the existence of this mode as saying that that we really just have a Fermi liquid, because I think that existence of this mode is really a general feature of any system that has a Fermi surface. There are some arguments you can make about deriving this mode just from considering the hydrodynamics of these conserved quantities associated with LU1. So I think the fact that you get this mode is just reflecting the fact that you have a Fermi surface. So in that sense, the model is successful in the sense that it's building in the constraints that need to be there from you have a Fermi surface. But you do also get these beyond Fermi liquid physics, like from these kinds of terms. You see we have this branch cut, which generally reflects some kind of strong coupling physics.
Okay. Can you be more precise how Q perp and Q parallel are defined? Because in building blocks of the theory, you only had a theta, which had no space dependence whatsoever. So how is this vector with respect to what vector are they?
Right. So we introduce the K Fermi, which enters the theory through this phase space magnetic field that we apply as a background to the we apply it as a background to the dual quantum field theory, which translates to the boundary conditions for the gauge field on the gravitational side. So the K Fermi enters that way, and then once you have a K Fermi as a function of theta, then that traces out a Fermi surface. So then you can define what you mean by the perpendicular and parallel.
Thank you.
Yep. So this second term is not what you get in Fermi liquid theories, and it presumably represents the fact that you still have some strong coupling physics going on in this system, even though you've built in the constraints from the Fermi surface. So this is the non-Fermi liquid behavior. And another interesting thing to look at is the optical conductivity. So this is where you set you apply a background electric field, and you measure the current, and you do it at q equals 0, but as a function of omega. And so you get these two kinds of terms. So the first term would also be, which is a pole at omega equals 0, would also be there in Fermi liquid theory. But again, I think that it kind of has to be there in any system with a Fermi surface. The conservation laws associated with this LU1 symmetry will impose that this term is there. But then we do have the second term, which is independent of frequency, which people often call incoherent conductivity. And Fermi liquid theory, you don't have this. So again, this is reflecting the non-Fermi liquid behavior. And then the first term is non-distributive, second term is distributive. So again, in Fermi liquid theory, in the absence of any quasi-particle scattering, which is like going beyond this LU1 symmetry, then it's non-distributive. So the distributive part has to come from the beyond Fermi liquid physics in this case. So yeah, that's all I have basically. So I presented these new holographic models which incorporates the essential physics of strongly coupled metals, which basically, by which I mean the Fermi surface and all the physics associated with that. I don't want to claim that this model is going to be, the answer that explains everything about experiments or anything like that. But, you're building in exactly what you need to build in, the Fermi surface physics. So I think it's hopefully going to be the right jumping off point to build new models. One particular direction which I'm interested in is that I said that this LU1 symmetry is emergent, so it means it can be broken by irrelevant operators. And once you do that, so the DC conductivity of this system is infinite, as you can see if set m equals 0, which is saying that the DC resistivity is 0. And that's because it's protected by the conserved quantities. But if you break these conserved quantities, which maybe by from irrelevant operators or something, then you can get non-zero DC resistivity, and then you can model transport and things like that. That's one direction I would like to explore more. Yeah, that's all I have. Thanks very much for listening.
Thank you very much. Yeah, thank you for this inspiring talk. I saw there was one question in the chat, again, only directed to me. It's a long question, so I asked Petro to either speak up or allow me to share this question. So while I wait for that answer, Petro, please let me know if I can share this with the with the public. Is there anybody else who has a question? Carl, please go ahead.
Let me see if this works. Hi, yeah, thanks for this very interesting talk. I would like to ask a question because I don't know if I missed it, probably you said it. All these non-dissipative terms, as well as this propagating mode, this linear mode, I think these are all, I would guess they are all proportional to the coefficient of the Chern-Simons term you added. Is that correct?
Yeah, so this first term is proportional to the, because M is the Chern-Simons level. The second term is actually independent of the Chern-Simons level.
Yeah. So just to make this analogy from what we know from anomalies, I mean, this is the first term I would call, what in this anomaly stuff we would call current magnetic wave. This is sort of the direct analog. You have also this magnetic field there, this d theta kf. So that's something quite general that appears with anomalies, that you have such a propagating mode in the magnetic field. Okay, just as a comment. So it's interesting to see that all this sort of, I guess this is a well-known Fermi surface physics, but it appears here like in the way we know from anomalies in magnetic fields. And my second question is, this was specific now to say a 2+1 dimensional quantum field theory with a Fermi surface.
Right.
So how would you generalize this going to 3+1 dimensions?
Yeah, I mean, there isn't much difficulty in generalizing it. I mean, the loop group symmetry changes because, the reason why it's mapped from a circle into U1 is because the Fermi surface in 2D is topologically a circle. For example, a 3+1D metal, the Fermi surface is a 2-dimensional manifold. So maybe you would want maps from the 2 sphere into U1. And then, so the anomaly stuff kind of carries over. Basically, instead of 5D Chern-Simons term, it will become a 7D Chern-Simons term.
But you have only one dimension more, not 2.
Well, you have one more spatial dimension, but then the Fermi surface is also one more dimension. Because you also integrate both over like the Fermi surface and over space-time, so you end up having 2 more.
But there is no Chern-Simons term, right? I mean, you would have, I was thinking you would need some higher form field, like a 2-form field.
No, the global symmetry is always a 0-form symmetry, so the gauge field is always just a vector field. You only have to increase the rank of a Chern-Simons term, so it becomes like A, dA, dA, dA. So 70 Chern-Simons term.
Okay, thanks.
I see Nicola has, please go ahead.
Yeah. Hi, thanks for the talk. Yeah, I was just wondering about your question, your future direction about gaining the DC resistivity. So usually when I would think of doing this, I would think of basically trying to give momentum some finite relaxation time through some axion field or something like that. And here you're talking about breaking the loop group. How does this relate to the usual way of getting sort of DC resistivity in holography?
Right. So, I mean, I think, yeah, I mean, it relates to the fact that we're describing the IR and not the UV. So in the UV, I mean, as long as you have continuous translation symmetry in the UV, you will clearly have zero resistivity because it will give you some kind of symmetry in the IR. And if you want to break it, then you would break that continuous translation symmetry. Which, in the IR, it's a little different in the sense that in the IR, the symmetry that protects the zero resistivity is not really momentum conservation. It's this loop group, because the weight of the delta Fermi hinge is protected by the momentum conservation is proportional to the charge density. And so since in the IR, the charge density is 0, there isn't really a contribution just from momentum conservation, but there is a contribution from the loop group conservation, which ultimately, of course, does relate to the conservation of momentum in the UV. But in the IR, it's reflected in the conservation of the loop group symmetry. So that's really the thing that you need to break.
I see. Thanks.
Any more questions? I have one question regarding probing this Fermi surface and this metal, because one question about 10 years ago was, how do we probe the Fermi surface of a Reisner-Nordstrom black hole, in the sense that like how do we excite in a way that we would do in an angle resolved photoemission spectroscopy experiment, electrons out of that Fermi surface and see what, like, map its structure. And that was a challenge. What was done at the time was just add probe fermions and see how they react to being in a charged environment like that. And I understand that was part of your criticism, and that's why you came up with this new model. So how would you probe the fermions in this model? Like, is that something that you have in mind, like what you want to do?
Yeah, so, well, it's a good question. You can add probe fermions, which are coupled to the LU1, which are charged on this LU1 symmetry. I'm not sure if that's really the right thing to do. Because it's kind of like whatever fermionic stuff is going on was already there before you introduce these extra fermion fields. So it's kind of like you just add in an extra fermion rather than probing the ones that were already there, which I guess is also something you could comment about this Reisner-Nordstrom case. But anyway, yeah, I mean, I don't have a great answer to that, because ultimately the thing about these R-pairs angle resolved photo emission experiments that you mentioned is that they're ultimately probing the UV fermion. Because it's an effective field theory, it's not that accessible to us in the IR. So yeah, I don't have a very good answer to that. I do think that maybe this is not answering what you asked, but there is some fermionic character to the system, even though it may not be obvious, because the level of Chern-Simons term, we choose it to be, well, in the simplest case, 1. And a Chern-Simons term with an odd integer level can only be defined on like spin C manifold. So there's something fermionic about it. So it seems like there are fermions somewhere in the system, but how to probe them, I don't know.
Thank you. Yeah, the same problem arises in the previous models. That's why I was wondering. But yeah, it would certainly be interesting if you found a way, if somebody would find a way.
Right.
Any more questions from anyone? Okay, so we have usually an informal chat after we close the session and the recording. So everybody who wants to chat for 5 minutes, just stick around. Other than that, thank you all for tuning in, and thank you, Dominic, for a very interesting talk and a clear talk with a nice new idea. And I hope to see you all next week. Thank you again.
Thanks very much.